Hi, Jose De La Portilla here. Thanks for tuning in. I want to talk to you today a little bit about motors, and I want to show you a cool trick I learned a long time ago from some of the old timers that saved my skin numerous times on jobs. And that's what do you do when you walk up on an older unit that has no nameplate, the stickers are faded, there's nothing attached to it, and the motor that you're working on has even lost its nameplate. Well, I've got a couple tricks I'm going to show you today that'll work to help you identify a replacement motor. I know there's a lot of universal motors out there, but failure to get the right number of speeds, the right rotations, or rotation's not as much of an issue because we can do universal rotation motors now, but what about horsepower and stack, those kind of things? Failure to get those measurements right, those replacement values right, can mean the motor doesn't run right. So let me show you a couple tricks I learned on how to identify any motor, even if it's missing its nameplate, and to find a suitable replacement for it. So in this video today, we're gonna look at the motor, we're gonna look at a meter reading that I've got, and then we're gonna zoom in on this TV behind me so I can show you some of the things that I want you to look for. So let's go through the process. First and foremost, if you're replacing a motor in our industry, and it's on a residential system, you're most likely going to deal with a PSC, a permanent split capacitor motor. If you've got a permanent split capacitor motor, how do you know it's a PSC motor? Well, it's going to have a run cap permanently connected to it. If you look at the screen here, it can either be one of those single pole run caps where it's just got two terminals, or it could be a dual run cap like you see in the second picture. But if you have a run capacitor, you know it's a PSC motor. Now, if you have a condensing unit or if you have a furnace that doesn't have a run cap, it's probably a pretty old system and it was using a shaded pole motor, and we're going to have to find a suitable replacement. A lot of times you're going to have to convert from a shaded pole motor to a PSC motor because you're not going to find those fractional horsepower shaded pole motors available in every place. So let's just say you know now that it's got a run cap, so it's a PSC motor. The second thing is you need to know whether it was a blower motor or a condenser fan motor. Now I'm hoping if you took the motor out, you know what it is, but what if someone took it out and handed it to you and you don't know where it came out of? Well, the simple thing is look, if it's got these vent holes all the way around it where I'm pointing it at to you, that means it's an air-cooled motor or an air-overcooled motor. This one is going to be installed typically in an air handler or a furnace with the vent shafts open to keep the motor cool. So whenever you see an open motor like this, know it's most likely a blower motor. If it were completely sealed on the top and on the sides, that's most likely going to be a condenser fan motor. So the first two things we need to know are already taken care of. We know it's a PSC motor because it had a run cap connected to it. And on this motor here, we see all the open holes, so we know it's got to be a blower motor. The next question that comes up is what type of bearing does it have? Now, there's two types of bearings in our residential systems that we use. One is a sleeve bearing, which is basically a sleeve that goes around this shaft that has a permanently lubricated wick or cotton seal in it that keeps the motor lubricated. Now, sleeve bearings are fine, they're low cost, but they don't handle a lot of stress or load. The other type of bearing we use is a ball bearing motor. They can handle greater load, greater torque, and they last a lot longer. If you have a sleeve bearing motor, it's perfectly fine to replace it with a ball bearing motor. It's actually preferred. The only thing that comes up when you replace a sleeve bearing motor with a ball bearing is they might be slightly louder with that bearing noise, but realistically, it's usually not enough to tell unless you're in a high precision piece of equipment used for like a mechanical room or a process room where they got servers, something like that. So if you have a sleeve bearing motor, no problem, change it out with a ball bearing. If you have a ball bearing motor, be advised, don't change to a sleeve, because that ball bearing motor was used because it needed to handle certain load and torque and stress requirements that a sleeve bearing can't handle. So, okay, let's recap. We got a capacitor, so we know it's a PSC motor. This one's open, so we know it's a blower motor. This one here happens to be a ball bearing motor, but if it was a sleeve, I'm going to replace it with a ball bearing motor regardless. Now, the next few things that you need to find out, even if the sticker is missing, just require a few tools. First is you need to have a screwdriver to take these through bolts out. And once you take the through bolts out, you're going to pry the end bells off and separate out the motor. Here we've got the rotor. Here we've got the stator, or the stationary part, with the coils of wire in it. And then we've got our other end bell. Let's just slide that out of the way. So the next thing that we need to figure out on this motor is what is its frame size, meaning what's the diameter of the motor. Now it's rated by NEMA frame size, and there's 3 typical frame sizes you can get: a NEMA frame 42, a NEMA frame 48, or a NEMA frame 56. Now, how do you know what frame size you have? It's just a matter of, if you look at that circle on the chart representing the motor on the TV, the diameter of the motor. The diameter of the motor equals the NEMA frame size. So, if we measure from here to here, we can quickly get an idea of what the NEMA frame size is. So, take a look at my tape measure as I do this. I go across here, and it looks to me like I've got about a 5.5 inch diameter across this motor. Okay, so again, I'm going from metal to the edge of the metal, 5.5 inch. So why don't you take a look at this chart up on the TV for me here, and notice that if you see 5.5, we don't really have that, but we got a 5.6, and if you look at a 5.6 diameter motor, that means it's a NEMA frame 48. You got a 48 frame motor. Now you say, but wait a minute, this one was 5.5. These are some approximate numbers. But if you look at the next biggest size, it jumps all the way up to 6.5 for a NEMA frame 56, or all the way down to 4.9 for a NEMA frame 42. So let's look at this tape measure again. Since it's right around 5.5, maybe a little bit over, I've got to say that this motor is a NEMA frame 48. Let's talk about it again. You know it's a PSC motor because it had a run cap. You know that it was a blower motor because it was opened. And because it's 5.5 inches, 5.6 inches roughly, you know it's a NEMA frame 48. You've got your values. Okay? Let's go on and look at what the next value is. You need to know the speed of the motor. So let's say this sticker that's normally on the side of the motor is completely gone, and you need to know the speed. There's a trick. The trick is to count the number of poles in a motor. Now, electrically, when we talk about a pole is a loop of wires. It's a loop of wires that starts in one place, as an example, here, and you see it loops over from here to here. Now it goes through on the back side and completes the loop as well, but the back side's usually harder to see because that's where we have the internal overload covered in this insulation. So we're going to go back to the front here and count our poles. Notice that there's 2 sets of windings in the motor here. This back one and this front one. One is a run winding, one is a start winding. To determine the RPM of the motor, we're simply going to count the number of poles or the number of loops of wire. And again, the loop starts here and swoops over to here. Now when you're counting the loops, you're not going to count the back one and the front one. You're going to count either the outer loops or the inner loops, the outer poles or the inner poles. So I'm going to choose to count the inner poles on this motor. And follow along with me here. I've got one that starts here, so that's 1 pole, 2 poles, 3 poles, 4 poles, 5 poles, and here's my 6th pole. So the number of poles, which are these loops or wires, is going to directly determine the RPM. So if you would, look at the TV here, and you'll see a drawing showing you how to identify these poles. And right next to that drawing, you're going to see the letters A, B, and C, and RPMs. So if it had 4 poles, 4 loops of wire, that motor would run at 1625 RPM when it's got no load on it. If it had 6 poles, it's going to run at 1075. And if it had 8 poles, it would run at 825. Well, when we looked at this motor, we counted 6 poles. So now we know that this is a 1075 PSC 48 frame blower motor. Okay. All right, we're doing pretty good. There's a couple values that we're missing. The next would be how many speeds is this motor, right? Because we want to make sure we replace like for like. Yeah, I know you might have been able to take the motor out and seen how many wire speeds were hooked up to know, but what if somebody else took it out, handed you the motor, and sent you to go get it? Well, to determine motor speed, the easiest way to do it is to look at all the wires. Okay. So I'm going to pull these wires aside. Now, the first thing that you would do is if you had a green wire, that's a ground wire. Take it and move it aside. The ground wire is not connected here because it was connected to the end bell of the motor. When we took it apart, we removed it. So you would get rid of the ground wire. The next thing you would do is get rid of the wires that the run capacitor would be hooked to. Now, normally they're brown or they're purple. Here I've got 2 brown wires. Those are my run cap wires. I'm going to take those and set them aside. Now I've got 4 wires in my hand. Now, one of these wires has to either be neutral or common if it was a 230 volt motor. I've got a white one right here. Seeing that it's a blower motor, I now know it's a 115 volt motor, most likely. So I'm going to take this neutral wire and pull it aside as well because that's the common side. That's the side that doesn't get switched. What I've got left in my hands are 3 wires, 3 hot wires. These are going to be 3 individual speeds. So I know I have a 3-speed motor. It's that simple. Remove the capacitor wires, remove the ground wires, and one of the other wires, whether it's a 115 volt motor, it's typically going to be a white wire. If it's going to be a 208, 230 motor, it might be a black, red, orange, but you're going to take one of those wires away because that's the wire that's going to be common, always connected. The remaining wires are our switching wires. So I've got 1, 2, 3, 3 speeds. So I know I have a 3-speed motor. Now, which speed is which? Well, there's a common chart that you can look on the TV and see. So if you look at this chart on the TV, it shows that the green wire that's color-coded is typically ground. The white wire is typically 120 volt neutral. A yellow or an orange wire is typically a 230 volt common. Black is typically high speed. Blue is typically a medium speed. Yellow would be a medium low, and red would be a low speed, while brown or purple are our capacitors. Now you might say, okay, I know a couple manufacturers that don't follow those color codes. So let's take a look at these meter leads again, or these motor leads again, and let me get my voltmeter out and show you another way to identify which one of these motor leads is what speed. This will help you know which one was connected to what tap. To do that, I'm going to get a voltmeter out here, and I'm going to set it to the ohm scale. So let me power up my meter here. And what you want to know is that the rule is the motor lead that is the highest speed or the fastest RPM is going to have the lowest resistance. Then as the motor slows down, the resistance of the winding will increase. So all I've got to do now is take my voltmeter leads, and I'm going to use these alligator clips, and I'm going to take one and clip it to my neutral or my common wire. Okay. I'm going to take my other lead and clip it to one of these 3 leads at a time to read the resistance. Now remember, the highest speed will display the lowest resistance. Let's see if it rings true. Because we said black was the high speed, so let's clip this on and read our resistance. Now 13.2 ohms of resistance. Okay, I don't know what that is yet until I compare it. Let's look at our next one. We said blue was typically a medium speed, so this should be a little bit lower than that 13.2. I'm sorry, a little bit higher than that 13.2, and it's at 19. Okay, there's the medium speed. Now we said red was typically the lowest speed available, so this should have a higher resistance than that 19. Let's see if that rings true. 24.5, 24.6 ohms of resistance. So did it ring true? Absolutely. Black, high speed, had the lowest resistance. Blue, medium, had a higher resistance. And red, my low speed, had the lowest resistance of them all. So whether you want to trust those industry standard color codes that we showed you on the TV, or you want to verify it with your own meter, you can, to determine what speed each winding was. Now I know, of course, if the motor's completely electrically failed or fried, that's going to be a harder test to perform because the windings are probably open or shorted. But if it was a mechanical failure, a bearing that went out, and you need a replacement, you can use that trick. Okay? So far, we've identified it. We identified PSC motor, blower motor because it was open. We identified the frame size, and we identified the RPM as 1075 by counting the poles. We've now determined the size, or the speeds of the windings. Now what we need to do is determine the horsepower. Now to do this, we're going to measure the height of something called the stack or the rotor. So let me slide that stator out of the way here. This is the rotor of the motor. It's called the rotor because it's the part that rotates, right? Where the stator is the part that stays still or is stationary. Now the taller this is, the higher the horsepower is going to be. Now the measurement I'm about to show you, you have to take into consideration are approximates. They're not exact because some motor manufacturers will change the height of their stack based on their efficiencies. So they're going to change a little bit. But what I'm going to do is I'm going to take my tape measure and I'm going to measure the height of the stack. Now let me just reiterate one point here. As you look at this here, you see the part here with the silver lines in it? From here to here is the stack. These extra pieces right here are not what we measure. This top and bottom portion we don't measure as part of the stack. So essentially what we're measuring is from here to here. So if we can zoom in, I'll try to hold this at a better angle so you can see my tape measure here. And I can still see it as well. I'm looking at what? Right around 1.5 inches, 1.5 inches, 3/4, somewhere around there. So the height from here to here is about 1.5 inches, 1 3/4. Now, how does this relate to horsepower? Well, I need you to look back at the TV and take a look at this chart. This chart is something that was given to me by a motor manufacturer years ago, but it still rings true. You look at the number of poles and you look at whether it's an open or a closed motor. So on the top left corner of this chart, you notice it says 4 and 6 pole open motors. We have a blower motor, which is open. This is a 6 pole motor, so it would fall into that upper left-hand quadrant. And we said it was around 1 inch, 1.5 inches in height, a little over 1.5 inches. So what does that tell me? If you look at if you look at 1/2 inch right there, if you look at stack height, 1.5, and you follow that to the left. So again, we're looking at stack height of 1.5 because we were about 1.5 inches to 1 3/4 inches, and follow it across. That would tell me you're running about a 1/3 horsepower motor. So I've got all of those values that I need to put in. I can now find my replacement. Now, you might say to yourself, well, can't I just put a bigger horsepower motor in? Not necessarily. Remember, putting a bigger horsepower motor in means you have more power, but you're going to utilize less of it. The analogy would be like taking a fancy sports car with a lot of horsepower in the engine, putting it in neutral, and then redlining the throttle. You'd have all this potential energy burning up, creating a lot of heat, but not doing enough work. Oversizing the horsepower on a motor can be dangerous to you. So that's how I would determine what kind of motor I had if the nameplate was missing. But don't take my word for it. Let's check the nameplate on this motor to see if what I had rang true. We said it was a 3rd horse. Look at that. Sure enough, it's a 3rd horse. We said that it was 1075, and it absolutely was 1075. Okay, we've got that there. We said it was a run capacitor because it had one connected, so there's our capacitance rating. Now you know what motor to replace. Now, if you come to linuxpros.com with those statistics and you look up our line of first choice motors, you're going to find a universal motor that'll fit your needs. If you prefer to go into the store, you can go to any of our Linux Parts Plus locations, which you can find by visiting linuxpros.com. Equipped with the knowledge that you have now, you can find a replacement motor. All right, now if all of this was too much to take into consideration or to remember in one video, don't worry, because we've got this sheet that I shared with you on the TV as a document you can download and throw in the back of your pickup truck or in your service manuals to refer back to. Everything's in there. So follow the link below, and you can download this as well to keep as a reference for yourself. Thanks for tuning in to this talk about motors. I hope you find it useful and informative. And I'll tell you, this has saved me multiple times when I had to change a motor on something that had no data. Thanks for tuning in. Appreciate you taking the time to listen to us. And please feel free to cruise linuxpros.com for our wide assortment of first choice motors to find the replacement you need. Thanks a bunch, and we'll talk to you later.